Oh, wait.
Okay, so let's start the last lecture of Tim.
Thank you. Okay, well, welcome everybody to the last lecture from Models to Data. I don't know exactly when the right time is to do this, but I would like to thank the organizers, and in particular Rogerio, very, very much. This has been a great experience for me in many different aspects. I've enjoyed the questions here from all of you. I've enjoyed the total environment. I've enjoyed Sao Paulo, so thank you very much. This has been really great for me. All right, so just very quickly where we are. I did not change the title of today's lecture, so we are going to forecast LSST and also talk about W first. And just as the quick recap, what we've done last time was we talked about the Fisher information matrix, and that is the theoretical foundation that we're going to use to forecast LSST desk, so dark energy science return. And just as a quick recap, so this is the definition of the Fisher matrix as it relates to the log likelihood, the second derivative with respect to these two parameters. So it tells you how fast does the curvature change. And the stronger this change in curvature is, the more rapidly it changes, the more constraining power an experiment has. So in principle, from this matrix, and we'll see, you can calculate something that's called the figure of merit. A figure of merit means how much information does your experiment have on a certain science case. Okay, if you're interested, so the Fisher matrix is the inverse of the parameter covariance matrix. However, when you compute Fisher matrices, you frequently use data covariance matrices. So those are important distinctions. You can also compute the Fisher matrix from the parameter covariance matrix, but there is not really a reason to do so. Usually it goes the other way around. You get the parameter covariance matrix from the Fisher matrix, and you've computed the Fisher matrix from the data and from the data covariance matrix. If you're interested in individual parameter uncertainties, these can be computed as defined here. So the uncertainty on an individual parameter, if you marginalize over all the others, is the square root of the inverse Fisher matrix diagonal element. And unmarginalized, if you're interested in just the uncertainty in that parameter, keeping everything else fixed, is defined as 1 over the square root of the Fisher matrix diagonal element. So for whatever reason, if people might be interested in that. This is the expression for the Fisher matrix for the case of weak lensing. And so you can see in order to compute the Fisher matrix here, you have to sum over the Fourier modes. If you're looking at a data vector that is CLs in Fourier space, if this is a correlation function data vector, you would sum over the theta bins times the inverse covariance matrix, and this is the data covariance matrix, and then again derivative of your observable with respect to the other parameters. So that gives you one element in the Fisher matrix, and you do that for all i's and j's, meaning for all parameters, and that gives you the entire Fisher matrix. Okay, so now we're going to use the Fisher matrix to reproduce a couple of things that were published in this document. So this is from the LSST Dark Energy Science collaboration, and it is a science requirement document. So in this document, you will find very specific answers to how well does LSST have to control systematics X, Y, and Z. Right? So photo Z uncertainty is one of our big problems. There is a requirement in there, how well do we have to model photo Z uncertainties. And that informs people who are working on these algorithms, who are developing photometric algorithms and who are processing these to photo Z information. And it also contains how well do we expect to do realistically on our core science case, and the core science case is, in this case, dark energy. So that was one of the main figures that came out of this exercise. And let's quickly walk through this. So why is this interesting? I've already mentioned a couple of arguments. So this is a pathfinder for a realistic analysis as DESC will do it on year 1 data. So year 1 data will arrive in 2023, maybe even earlier, but 2023. And it's going to be a fantastic data set to work with. It will be 18,000 square degrees altogether. It will be already deeper than DES data. and it will be taken by a telescope that is, well, let's face it, a bit better than, for example, the DES telescope. And that's very soon, 2023. It's quite scary. And even before that, there will be science verification data. And science verification data is also interesting of LSST. That's just a 3-month or 6-month observation. I think it's 3 months. It's 1,600 square degrees, but it goes deeper than DES already. So this is already going to be and that arrives in 2020. So that will already be a data set that is competitive with the best data sets that we have around right now. And then 2 years later, it'll be very, very, well, even more better. Okay, so what you can learn from these Pathfinder exercises is how do you model observables precisely, right? You need this to compute these constraints, so you already explore how to model observables. In order to get requirements on systematics, you also need to understand how do you model systematics. That's a question you need to answer here already. And maybe there's different options for how to model systematics. Modeling of covariance matrices. I've shown that the Fisher matrix definition for weak lensing requires a data covariance matrix. And that's also true for all the other probes. So you have to deal with covariance matrices. You have to build them. Otherwise, you can't run such a likelihood analysis or such a Fisher matrix analysis. And you have to understand which scales require which kind of systematics parameterization. So when you define exactly what goes into this analysis, you will have to make choices like, do I include very small scales? Do I only include very large scales? If I go to very small scales, what kind of bias parameterization do I include? What kind of intrinsic alignment parameterization? What kind of a mitigation scheme for baryonic physics? So all of this is stuff that you have to think about when setting up such an analysis, and the whole collaboration of DESC came together to actually define these. The other problem that you have to tackle is inference in high-dimensional parameter spaces. So yes, we only show WA, W naught here, and actually only delta WA and delta W naught, so they're both centered on 0. But there's obviously many, many more parameters involved in these analyses. And the higher dimensional this parameter space is, the more difficult these problems become, so you have to solve these as well. And all of this is not wasted. All of this is going to be useful for the actual analysis as well. So that's one of the main reasons why I would also encourage junior people to get involved in these simulated analyses. You can map out you basically map out everything that is needed for the later analysis as well. Okay, so once you have all that machinery, what can you do with it? You can do trade studies of systematics impact. You can say, okay, my photo Z priors, let me degrade them a little bit more, but then I assume that I can do better on shear calibration. And you can see how that changes. And you see correlations between these different systematics. It guides the development of software pipelines. That's very important because, people are being paid in order to develop these software pipelines. It's not necessarily, well, it is not yet exactly clear who is developing the software pipelines for DESC. I think it's mostly going to be scientists, but if you look at the Euclid collaboration, scientists do not do software development. That is done by professional software developers, and the scientists are only allowed to check the code, which is, in my opinion, not the, well, maybe not the best approach, because scientists usually are excited to develop their own code and see how it works. But yeah, I guess if you are a very large collaboration and have these resources, then that can make sense. Obviously, professional software developer makes less mistakes in coding than a scientist. I can vouch for that. Right, and you can identify commonalities, so things that are in common between the different DESC probes. So usually if you look at the structure of DESC of the collaboration, and there is a weak lensing working group, there is a large-scale structure working group, there's clusters, there's supernovae, they don't necessarily talk too much to one another. They're kind of having their own environment. But if you have to bring it all together, then this is an exercise that does that. This exercise brings all of them together. They have to sit at the same table and make all of these analysis choices. So I learned a lot about supernovae, to be honest, in this case. And you can do survey strategy studies. And that's actually going on right now in DESC. The survey strategy of LSST is not yet set in stone. There's many different ideas. There's also competing interests from the different science collaborations. So people who want to study the galactic plane obviously want the telescope to point there. People like me who are more interested in cosmology want to stay away from the galactic plane, only want to do the extragalactic sky. So those are, so you can do these trade studies. What happens if LSST points the telescope 90% of the time to the extragalactic space? What if it goes wider? What if it goes deeper, etc.? Okay. Let's have a quick look at what is depicted here. So I said already parameters W0, WA. There is in yellow the strong lensing year 10 constraints. So strong lensing as a cosmological probe perhaps not quite as constraining on the dark energy parameters as they are parameterized here. So just W0, WA, no principal component, no other sophisticated evolution. Clusters in blue. Mostly affected also by uncertainties in the cluster mass observable relation. That is one of the main problems that's one of the main systematics that clusters have. This here in red is the combined power of all stage 3 surveys. So that means Planck, BOSS, joint light curve analysis. I think there was even something else in there. If they were all to perfectly agree, you can combine them, you get the red contours. Supernovae in green. And 3x2 points, so that means galaxy-galaxy lensing, galaxy clustering, and weak lensing in blue. And then there is another experiment, purely spectroscopic, which is DESI. So DESI BAO plus Planck, that gives you these contours over here, quite nice. And LSST altogether gives you these very small ones. And so the reason why these contours here become very, very small, if you throw all of this information together, a fair fraction of that comes from the combination of supernovae here and 3x2 point. And then because they are orthogonal to another, they break the degeneracy in W0, WA parameter space. And so the combination of these two, just because they are so nicely orthogonal, that gives you some very, very nice tight contours. And then in addition, you get clusters, but you can see clusters here is somewhat aligned with 3x2 points. So there is an increase in information, but it is not as groundbreaking as if you combine things that are orthogonal to one another. Okay, so quickly DESC terminology. Yeah, so there is a DESC SRD, but there is also an LSST SRD. And there is the connection that LSST is the big telescope and it has its own project, and DESC is a science collaboration, and that's just not the same. So both of them have created their science requirement document, and they have taken great care not to walk into each other's territory. So but just if you talk about the SRD, don't confuse it with the LSST SRD. That was something that was relatively important. Stressed to us all the time. So objectives that are mentioned, big picture scientific motivation for DESC. That means we want to do dark energy and we want to do it better than anything else. High-level requirements, those are directly associated with the objectives, and that is, so let me make an example. Here, we want to do dark energy extremely well. This means the Fisher matrix figure of merit needs to exceed a certain threshold. That's a very specific requirement. And then detailed requirements, they are being set on the individual probes, like weak lensing. Weak lensing needs to be better than X, Y, and Z. Shear calibration needs to be controlled better than X, Y, and Z. And then there's goals that are things we want to achieve, but it is not a prerequisite. So sometimes collaborations identify goals rather than requirements, because then when they are being asked by the funding agencies, have you achieved those requirements? They can say, no, they're just goals. They're not actual requirements. So that is sometimes very handy, because these are hard to calculate and they're hard to achieve. So you want to be a little bit vague here. That's just smart. Otherwise, in the eyes of a funding agency, you have failed. And that's not a situation you want to be in. Okay, systematics terminology. So we already learned there is many, many different systematics. And so here is what DESC has done. We have defined two very broad categories: self-calibrated systematics and calibratable systematics. I didn't come up with this. I apologize a little bit. for this. So these are being self-calibrated systematics are what you would know as astrophysical systematics, like intrinsic alignment, galaxy bias. Those are things that we hope that the data itself will calibrate them. So we give it a parameterization, but we don't put strong priors on that. We hope that the data tells us what this is. This is something that we need to control very well, and we can control this well by developing sophisticated algorithms, by using external data sets, etc. So this is where we put requirements on. Shear calibration needs to be better than. Photo Z uncertainties need to be better than, etc., etc. And then also important are some scale cuts that have been made in this analysis in order to exclude, for example, baryonic physics. So baryonic physics is not modeled in these analyses, and we justify that by having some conservative scale cuts. Okay, so here's an example. Objective LSST will be a key element, blah, blah, blah. And then the requirement that corresponds to that the combined figure of merit should be 500. So what, and I'll get to that in 2 slides, what the figure of merit actually is. But given a Fisher matrix, you can calculate the figure of merit. So the Fisher matrix tells you how well does your experiment do, but you can condense that information of a largish matrix into just one number. That's very convenient, right? And that's the constraining power of your experiment, figure of merit. And then let's have a look at, oh no, that is sufficient. Let's stay with that. Let's have a look at a detailed requirement. So if you parameterize your redshift uncertainty, say we have this z dn dz, and we have this nice redshift histogram. So we have separated this into many tomographic bins, and you characterize each and every one of these tomographic bins with the mean and the spread. Then you can say the uncertainty in the mean redshift of each source tomographic bin should not exceed this number. And that's something that you can set as a goal, and it's something you can test. You can test it with existing data. Do you actually achieve this precision? You can test it with simulations, and you can test all of your algorithms whether they actually achieve this kind of a goal. So those are the very specific kind of requirements that you can find in this lengthy document. And we'll get to how they are being set. Now, if you dig deep into systematics, then you will find that there are all sorts of contributors. And here is an example for 3x2 points, so for the joint analysis of clustering, lensing, and galaxy-galaxy lensing. And let's go down this route, for example. So multiplicative shear is the uncertainty associated with how well can you measure shapes. And there's a couple of contributors. For example, how well can we do star-galaxy separation, right? How well can we do PSF modeling errors, etc. And ideally, we would be able to put requirements on all of these very, very detailed aspects. Unfortunately, we're not having that sophisticated a machinery right now. We're kind of stuck at, well, at this level, and then sometimes we can poke a little bit into the more detailed aspects. So we kind of know how much our PSF modeling uncertainty contributes to the multiplicative shear error. But ideally, in the long run, when it will be more people computing these requirements, we will be able to actually explore these systematics as well. Okay, so how do you compute this figure of merit that I've mentioned the whole time, saying that like, it has to be larger than 500? Well, we only consider dark energy constraints here. So we only consider W0 and WA. And in terms of this dark energy task force figure of merit, this is defined as the determinant of the Fisher matrix, of the square root of the Fisher matrix. That is the figure of merit. So FOM is right. So you compute the Fisher matrix, calculate the determinant, you get the square root, you get this number, and this number better be larger than 500, otherwise we've failed in the eye of NSF and DOE. So that was, I mean, it is quite funny. When I started out doing these computations, and I was mostly responsible for this part over here, supernovae came from René Schlotzek, and strong lensing came from Tom Collett. Then basically we knew what to achieve already, right? We were not allowed to end up being below 500. Right, so this was stuff that was done with Cosmology, and I got this information from the two people I mentioned, and then combined everything in the Fisher matrix, and that's also what you've downloaded in this repository and what you can actually reproduce. So just very quickly, of course, you need some kind of sophisticated machinery to forecast your observables, right? And this is an illustration how it is done for what is called the static probes. So, you know, strong lensing, somewhat variable. If you do it with quasars, those are variable sources. Supernovae is also a variable source. And so the definition was for everything that is not those two, we consider that the static science. Because weak lensing doesn't really change on a time scale that's relevant for us. Neither does galaxy clusters, and neither does cluster weak lensing. So for these static probes, you can start out from cosmological parameters. You compute a 3D power spectrum. And then for weak lensing, you go down here to the projection functions. You project the 3D power spectrum. You get the projected power spectrum, the CLs. That is true for weak lensing, this route. It's true for galaxy-galaxy lensing and for galaxy clustering. At various points in these calculations, you have all of the systematics that are entering. This is somewhat a mapping of the code onto the physics, right? So these, this is actually a very large file that is part of Cosmology, cosmo2d.c. I think nuisance.c has been renamed to systematics.c, but okay. Shear calibration, photo Z, intrinsic alignment, baryons, bias, HOD models, they enter at various points. And then you feed that into the Fisher module or into a likelihood function, and you get a covariance matrix that comes from a different route. But then you can get the posterior probability, or you can get the Fisher contour. So I'm not going to go through many more details here. Well, this is the cluster route up here, and then you get the number of clusters as a function of mass and redshift. And that also enters, and then these two are combined for a data vector, and both of them enter this likelihood computation. And the covariance matrix is a whole different beast, which doesn't fit on this slide. This was the covariance matrix for LSST year 10. So you can see up here, this is cosmic shear. If you zoom in, each and every one of these dots is actually its own matrix. I think it was so each and every one of this is like a 15 by 15 matrix. And then there is, well, in this case, we only had 5 tomographic bins. The galaxy clustering working group wanted to have 10 tomographic bins as lens sample. So that became rather large. And then consequently, because you have so many combinations of lens and source bin, galaxy-galaxy lensing becomes a very large fraction of the matrix as well. Galaxy cluster number counts, we only had 4 richness bins, so that is relatively small. And then again, if you use cluster weak lensing, so you take the clusters in the foreground, you combine that with the sources in the background, that again is a slightly larger part of the data vector. So computing this covariance matrix for LSST year 1 and also for LSST year 10, that was one of the major tasks. Okay, and then the two forecasting results, and what is shown here is the 68% confidence level in the W0 WA plane, and that corresponds, that corresponds to everything that you can see here. For this is year 10 and this is year 1, and I put them on the same scale such that you can see the improvement. So already year 1 is going to be really interesting. Okay. Right, I already mentioned this. So when we computed, so the requirement was to have a figure of merit that is larger than 500. When we did the computation, we ended up with 625 after year 10, and actually just 94 after year 1. So what you can see from these two numbers, and if you compare that to these two figures, you will see that they don't necessarily scale exactly linearly. And the figure of merit is known for that. It is not something that is really scales very, very linearly in terms of information content. So there is, yeah, it is. I just want to convey that this is a little bit of an arbitrary measure. I would not necessarily read too much into something having to be larger than 500. That was an arbitrary number that was set by very important people, and so at that point it doesn't become arbitrary anymore. Okay. So how do we set requirements? Well, so first of all, so this plot is something that you've seen already, right? If we do the Fisher matrix analysis, just like this, you will get a contour that is centered on the true input value, right? Now, if you want to know what kind of a requirement is needed for my experiment not to be, contaminated, not to be affected, you contaminate the data vector with some kind of a systematic S. So you add shear calibration to your data vector, and it's contaminated. Okay, that will introduce a bias, so the best fit will be up here. And you compute this parameter bias, and that can also be done in the context of this Fisher matrix formalism. You find the ratio of this bias and the 1 sigma contour. Because this is now where you can make some decisions, right? You can say, okay, my bias is not supposed to be exceeding this contour. That's tolerable for me. Or half of this contour. That's tolerable for me. But it is important for you to understand what is this distance, and we've quantified this distance in terms of multiples of the 1 sigma region. So then you compute the ratio of this bias that you've gotten with respect to this 1 sigma region. So basically, if this ratio S to R is just 1, then the bias sits exactly on this 1 sigma contour. But that's only one systematic that you've checked up on right now. So we consider all the different systematics individually, one by one. First shear calibration, then photo Z, then et cetera, et cetera. And we assume that they all add to our systematics budget. So you don't want each and every one of them contribute 1 sigma. You would perhaps like each and every one of, or all of them together to at most be 1 sigma. Right? So basically, when you add them all up, you don't get something that's very far away. In the worst case scenario, you never know, they might also balance each other. That is entirely possible, but we're considering worst case scenarios here. Now, in our case, we did not say that the sum of all of these systematics has to be smaller than this 1 sigma region. We actually said it has to be smaller than the difference between our requirement, which was 500, and the actual number that we got after year 10, which was 625. So we basically created this systematics budget over here. This is 625, and that is then a combination of statistics, what we can tolerate, plus then systematics. And that allows you a systematics budget of 0.62. So the sum of all of this divided by whatever error you have here should be smaller than 0.62. And then there was a huge trade space going on with, like, the supernovae people needed a little bit more of the systematics budget, and then the weak lensing people gave them a little bit of their systematics budget, et cetera, because this is for the joint analysis, right? But now there is, in this particular document, a requirement that, or there are requirements that if you add all of them up, you still reach a figure of merit that is 500. And that's the main goal. So even with all the systematics included, you still reach this figure of merit. I should say that if you at some point start looking into the literature and you compare different, different types of these analyses, how well is survey X going to do compared to survey Y, you really have to dig into the details, what went into these analyses. Some of them just don't consider systematics. Some of them make very, very optimistic choices about systematics. So one has to be careful when comparing these numbers. And of course, if there's different experiments who are trying to be funded, then there is frequently a race in these kind of figure of merit things, and people start assuming non-conservative or start making non-conservative choices. So that's just a word of caution for you to look very, very closely what went into such a systematics analysis. Okay, this is the topic. So next, for the second half of the lecture, we'll talk about W first. But now I actually wanted to do some coding. So if you could take out your laptops, and we will do some desk SRD code. Let me see. So this is the, sorry, let me quickly turn this around a bit. Yeah, I guess I can live with that, thanks. I live dangerously, yes. Okay, so let's have a quick look at this repository that you guys were downloading as well. And I just wanted to mention a couple of things that are going on here such that it is easier for you to follow, perhaps. So first of all, there is run data. What happens here? Who can quickly describe what happens here? Who knows already what happens here? I don't know if you've... Okay. So what happens here is you compute all of the data vectors that are later needed for the Fisher matrices and for the requirements. So this is just, you call the pre-computed executable like Fourier with some arguments, and this first line, for example, will give you the weak lensing data vector, the fiducial one. The second line over here gives you a contaminated data vector that is then, well, okay, I have to improve my living dangerously here a little bit, sorry, because I might have to leave this place to the blackboard, and then I don't want it to crash. Right, so we already talked about fiducial and bias, right? Okay, this also has a contour, but we don't really care about that. So in order to get this bias, in order to calculate this properly, I need to have a contaminated data vector, and that is being done in the second line. And then this one here gives you a contaminated data vector where the mean photo z is being shifted around. The third one is where the sigma is being changed. So in short, you're computing a bunch of data vectors here for different probe combinations. This is weak lensing, this is galaxy clustering, this is clusters, this is 3x2 point, this is all of it together, and this is the same thing for year one. So that is happening here. Now, how do you get this file that does all the magic things? Well, that is like Fourier.c, and that's one of the things that get compiled when you make Cosmo-like. So if we go to the very bottom of that, you can just see what happens here. If the argument is fiducial, then it computes a year 10 data vector. It calls it Y10 fiducial. And there is an enormous amount of numbers that go into this. And I mean, I'm not going to explain them all, but maybe this one is omega matter. So this is the cosmology that is being assumed. This is the amplitude of intrinsic alignment that is being assumed in this data vector calculation. This is H0. These are various, these are various photo z uncertainties. And then at the, is it photo z? Yeah, this is photo z, and this is sigma z. So you can see 10 zeros in the fiducial case. There is the assumption that there is no shift in the photo z parameter. Okay, so that's just what happens here, and I'm not going to go into the nitty-gritty details of other ingredients, but I wanted to give you a quick impression of how this code works. So it calls a routine compute data vector, which is over here. There is a bunch of information that is being set. You have to identify the binning. The binning has been predefined as well. Here it sets the individual data, the individual parts of the data vector, depending on what choices you've made. So if it's just weak lensing, then only this one here is being called, et cetera, et cetera. And then these data vectors are being written out in a folder called data v, and you can see that here. So those are all the different data vectors that are then being written out. And if you want to have a look at them, they're in this very inexplicable format of having a cardinal number and then some cryptic number, and that is the, so that's the data vector. And this is just the nth bin that is being included. If you want to know what L and redshift this corresponds to, you'll have to read the README. That's where this is actually explained. Okay. So here, for example, those are the L values that were included. This was 20, okay. Not 15. And, well, the redshift binning is usually, yeah, the redshift information can be found here. So these are the redshift files. This is the source sample for year 10. This is the source sample for year 1, lens sample year 1, lens sample year 10. So those are the four main, those are the redshift ingredients that are needed. You just need 2, depending on if you want to do year 1 or year 10.
So is this log binning?
Yes, this is log binning, yeah. So this is log binning between, interesting. Right, 15,000 and 2,000. Now, why 15,000? 15,000 is not something you should go to in a weak lensing only analysis, and the corresponding bins are being set to 0. But when you do cluster weak lensing, where you look at very, very small scales in the one halo regime, you actually do want to go to these high values. So that's the reason, and there's, and you don't want to have a different binning for cosmic shear and for cluster weak lensing. That just gets very, very messy. So in order to have a homogeneous binning throughout the whole covariance matrix, you pick 20 bins that go from something low to something very high, and then for cosmic shear, you exclude the corresponding bins. Let me actually show you that. It's a very good question. Where is the covariance matrix? Wait, where is the covariance matrix? There we go. So here, you can actually see that there are some white gaps in here, right? This is one covariance matrix that goes from the first L bin to the last L bin. So this should be 20 by 20, but there is some white area where bins have been cut out, and that's because here in cosmic shear, you set these very, very high bins to 0. So cosmic shear only goes to L of, it includes this bin, this 15th bin, but it does not include this one.
So the size of the data vector is 1300?
Maybe.
That's not the matrix.
Yeah. I just don't remember. It says, yeah, that would be, yeah, roughly 1375. Now I actually remember, yeah. Well, we've definitely built larger matrices already. Currently for W first, we're building one that's 3,000 times 3,000. And there is various, it's not necessarily the size that makes it so complex, but really which kind of probe combinations and which L bins you actually include that can destabilize such a matrix. So there's a lot of playing around and fine-tuning involved when you do that. All right. So, wait, cursor, come on. Right. Okay, I hope that was helpful to explain what happens in this very first step. So you compute the data vectors itself. And then there is this one, run Fisher. So run Fisher, I mean, it's quite obvious. You just run the Fisher matrices. And again, what happens here is you give it some arguments. Year 1, you tell it what probe combination, and you say what kind of a contamination you're looking at. And then the code will automatically use the right contaminated data vector, and it will calculate this ratio, and it will calculate the figure of merit for the corresponding probe if there is no contamination. So I think it's doable to just run one. So I'll just do that here, but let me bring that. So I've now excluded all of the others that you probably ran overnight and then it took a little bit longer, especially for the ones where you have these very large data vectors, the ones where you include galaxy clusters, and you have to compute derivatives of galaxy clusters with respect to different parameters. That just takes forever. So this one should actually be rather fast. I'm not sure. I cranked up the precision for these computations a lot. Maybe I should have relaxed some of those. But so this is this parameter here is the step size for the numerical derivative. So that is basically the separation in parameter space with respect. So you define min and max in parameter space, and then you divide that. Yeah, okay, and then actually this number doesn't directly translate to something that's meaningful. But what I did here is so in order to check for convergence, I actually went from step sizes that here correspond to 5.0 all the way down to 0.1 in steps of 0.2 and computed Fisher matrices all the time. And then I look at the output. And what you will see is that the output at some point converges and then again goes haywire. And that's when the step size just becomes way too small. And that's the problem in the Fisher matrices. And anybody who's doing Fisher matrices should do that kind of an exercise. So vary your figure of merit as a function of the step size in the derivative. Also use some serious derivative. Don't just do a 2-point derivative calculation or 3-point derivative calculation. And check for convergence. And you will not see this plateauing off, because when the step size becomes too small, the whole thing goes bogus again. So there, you will have to make a choice what you believe in that case. Okay, now, this is actually taking too long. So let's just look at the output that I had before. That was over here. Ta-dum. This is the figure of merit. So it's 273. For weak lensing, wait, what was this? Was run Fisher? Yeah, this was just, no, this is 3x2 point. Okay. This is too large for just 3x2 point. Ah, no, this is just 27. Sorry. Okay, 27. Yeah, that makes sense. So this is just 27 for weak lensing year 1, and this is if you include Planck information. What you get. So if you include some prior information, and at that point in time we weren't sure, should we include prior information directly in the figure of merit computation, or should we just use the desk-only ones, and we decided to go for the desk-only ones at the end. But this is the relevant number. This is exactly this. So the code computes the Fisher matrix, then takes the determinant of the Fisher matrix, and takes the square root of that. And the Fisher matrix, again, is obtained basically by taking derivatives with respect to the data times inverse data covariance matrix times times the derivative with respect to a different parameter, derivative of the observable with respect to a different parameter. Okay. So if you wanted to compute a different data vector that is differently contaminated, you would change one of these values. Sorry, down here. If you want to compute a data vector at a different cosmology, you would change your cosmology here. I could have made some very nice, interface that does that, but unfortunately, there was no time. There really was no time. This was a very intense 2 months in order to get this to the desk leadership in time. If you wanted to contaminate your data vector with a different shear calibration uncertainty, you would actually change these numbers over here. Any one of them. Ah, yeah, actually, this is interesting. So why are they all different? Well, we have 10, no, actually, we only had 5 tomographic bins here. So it's just the first 5 of these numbers that are active. And we assume a redshift-dependent shear calibration. So we assume that depending on which tomographic bin you go to, from here to here to here to here, you have a different shear calibration uncertainty. If you don't do that, if you assume that the shear calibration uncertainty is the same in all tomographic bins, you really change the requirements quite a bit. So what we found was if we did that, weak lensing is already solved. The requirements are so loose that they are already solved nowadays. So that would not have been a very conservative approach. So we looked for a behavior of shear calibration that that basically causes a larger bias and that consequently puts a more stringent requirement on how well we have to control it. And that's an important lesson to learn. The way how you parameterize these systematics will change your requirements, right? So if you make a general statement, shear calibration needs to be better needs to be better controlled than X, Y, and Z, there's always a follow-up question, well, how do you parameterize shear calibration? Do you assume it is constant as a function of redshift, or do you assume it varies? Okay, so that would be the way how you get differently contaminated data vectors, and then you can compute requirements for those as well. Was there something that I wanted to mention here? Okay, these are the different Fisher matrices as notebooks. You can actually import them directly into IPython if you want. Yeah, I don't think I have time to say much more about this here right now. But are there questions about this? Okay, maybe perhaps this. Yeah, okay, covariance, fine. Yeah, so covariance matrices, they're all stored here. Now let's have a look at a covariance matrix. So this is the year 10 covariance matrix. The relevant columns are here. This is all explained in the README. I didn't do documentation here in these files. I should have done that. I'm sorry, but again, time. These are the covariance matrix. This is the Gaussian part of the covariance matrix. This is the non-Gaussian part of the covariance matrix. So Gaussian covariance matrix, we've not really talked about this, but the Gaussian part of the covariance matrix means that you can express this in terms of the power spectrum itself. So if your observable is a power spectrum, there is your covariance matrix would actually be a 4-point function, right? The power spectrum is a 2-point function already. The covariance matrix would be something quadratic. It would be a 4-point function. But there is if you assume a Gaussian shear field, there is Wick's theorem actually, and you can contract the 4-point term into just 2-point terms. That is not 100% precise. So if you include the non-Gaussianity of a covariance matrix, you have to calculate a 4-point function properly, and then there is something else that's called supersample variance. Also have to that also counts towards the non-Gaussian term, and you get a lot more off-diagonal terms than you would otherwise get. If you were just to look at the Gaussian part of the covariance matrix, you can see there's a lot more zeros. And for some regions in parameter space, you can see that the non-Gaussian part is actually larger than the Gaussian part. So it's not entirely negligible. And it depends on many, many different aspects, which of them dominates, and whether you should include them or whether not. It depends on the probes, it depends on the binning, it depends on the number density of the galaxies, because the number density only affects the Gaussian part. If you have very large number density, then the Gaussian part gets relatively small, because it's basically scales as 1 over number density squared. 1 over number density plus 1 over number density squared. And so if the number density gets large, this thing gets very small. And that also depends on the number of tomographic bins that you have. So for example, if you just have 1 tomographic bin, the number density in that bin will be very large. If you have 10, then per bin, you will have fewer galaxies, right? So it's a lot of considerations that go into whether you should use a non-Gaussian covariance matrix or not. This one computes kind of instantly. The Gaussian one, it's just power spectrum, and then you multiply power spectra, it's fine. This one takes quite a long time, and also different contributions here take longer than others. Okay, so those are the 2 relevant columns. You would have to add them. For simplicity, the first 2 columns, they are just they're just the index. So if you want to plot the covariance matrix, you just plot ij, and the sum of these, and you're done. So that's how you actually get the other plot. And they're not ordered, but I can assure you there is a 0, 0 somewhere here in this file. And the reason why they're not ordered is because when you compute one of these, you actually parallelize the individual parts of the covariance matrix. You farm them out on a supercomputer, and then you get lots and lots of files, and you just mush them all together, and then you get something that is unfortunately not ordered. That's the main reason. This is the L bin, L1, L2, and these are the redshift bins. So a covariance matrix is an argument of, in this case, covariance matrix is L1, L2, Z1, Z2, Z3, Z4. And only certain combinations of Z1 and Z2 are allowed, and Z3 and Z4 are also allowed. So yeah, this is described in the README, but you can see there's 6 arguments, there is correspondingly 6 columns, then there is the result, and the first 2 are the indices. So if you want to plot it, it's actually quite straightforward. Also, if you want to invert it, there is an inversion routine that comes with it, but you don't have to because I've already inverted all of them for all the individual probes for you. And so this is just the index again, and then the inverse covariance matrix. And there is a bunch of subtleties that are mentioned in the README file. I won't go through them here because I actually would like to talk about W first. So if you want to, so if you do run Fisher, that actually calls fisher.py. That's where all the magic happens. And this is in Python, so people who are younger will be very happy about that. And you can see this is where the different initialization routines for the different cases are happening. Blah, blah, blah. And then it's, right, and that's also where the inverse covariance matrix that corresponds to this scenario is being read in. So if you are interested in calculating the year 10 Fisher matrix, year 10 Fisher matrix, this is going to be called, and it will call the right redshift distribution, it calls the right covariance matrix, and it does all the right settings, and then it will go here, next, get Fisher matrix. And then it will compute the figure of merit. Yes, please.
How do I define the parameters that I want to analyze?
So the parameters you want to analyze in the Fisher matrix, well, that choice unfortunately has been made for you here. So
It has to be those parameters that you
yeah, so the Fisher matrix that is computed here, okay. Right, how do we do this best? Let's have a look at one Fisher matrix. Okay, we have to look at Fisher all. Okay. Yeah, because these NumPy things you can't really look at. Okay, so this is a Fisher matrix for year 1 3x2 point. Now you're seeing lots of numbers here, right? If you look at one of these arrays, what is this 3x2 point? Why is that so few? 1, 2, 5. Is that so few? This is. Okay, so basically the year 1 Fisher matrix for 3x2 point includes 7 cosmological parameters: omega matter, sigma 8, ns, w0, wa, h0, and omega baryon. And then shear calibration uncertainty, that should be another 5. And then photo Z uncertainty, that should be another 5 parameters. So, and then you can contract this Fisher matrix, as I've mentioned. If you're only interested in W0, WA, you have to invert the Fisher matrix. You just pick those columns and rows, W0, WA, and then you re-invert it again, and then you compute the Fisher matrix figure of merit. Then you have the figure of merit that is marginalized over everything else. But yeah, you can't really, so unless you want to dig really deep into the code, and this is something where you would have to change almost everything. Within the given parameters, you can make different choices, right? If you want to have the Fisher matrix for not W, not WA, but for omega matter sigma 8, you can make that choice. But if you want an entire different parameterization, you will have to dig almost all the way down in the code. There's no easy solution. But if you have something specific in mind, I'm happy to talk about it later. Okay, so this is where the Fisher matrices are being written out to, and then they can be further processed. Yeah, I really want to talk about W first. Are there any other questions about this repository? Was this, could you somehow map these ingredients to what was covered in the lecture? Like how do you get a data vector, how you get a covariance matrix? Okay. Are there any other desperate questions of people who are like, I didn't know anything what to do with these? Okay, if you have questions about this repository, do have a look at the README. It does explain really most of the stuff. Rachel made me explain everything that I used, Rachel Mandelbaum, so you can thank her for these explanations. But there's really lots of details here, and most likely you will find everything that you need. Now, if you have such a Fisher matrix, and that's the last thing that I wanted to show. If you have such a Fisher matrix, you can invert it, and if you invert it, you get a parameter covariance matrix. And the parameter covariance matrix you can actually use to run a chain. So let me quickly check. I hope this is the right one. Yeah. So if you're interested in running a chain very, very quickly, you can take these Fisher matrices, you invert them, you get a covariance matrix. Actually, you don't even have to invert them because you want the inverse of the parameter covariance matrix already. So that is the Fisher matrix. You can just read in the Fisher matrix here. And this is a routine that allows you to compute the log likelihood of the SRD LSST year 10 3x2 point analysis immediately. So you just set, this is the, so you just take a sampler that gives you a set of cosmological parameters. You take the difference of these cosmological parameters with respect to the fiducial value, to the input value. You have your Fisher matrix here. That is the inverse parameter covariance matrix. And then here you just multiply them. That's all it is. It's just this very, very small snippet. And that returns the log likelihood. So you patch this together to a sampler. The sampler just varies these guys. And then you can just run a chain in this a 7-dimensional cosmological parameter space. And you can plot that at the end, and it will look like an ellipse. It has to look like an ellipse because there's no, actually, well, it will look like an ellipse. Okay. So that was just to connect basically the Fisher matrix part that we had to the sampling part. And what are samplers that are commonly used in Python? There is, for example, MC. If you just Google MC, and MC is also something that I'm using. It's a parallel MCMC sampler. It's not Metropolis Hastings directly. You can get such a chain. With this routine, you can get it within minutes. Within 5 minutes, you get 1 million steps. Now, that's much easier than if you have to compute the data vector every time. Okay. So much about this repository. So in principle, you can now reproduce these Fisher matrices. But I wanted to talk a bit about W first at the end. Yes?
Is there a similar package for supernova science?
For supernova science, like what do you exactly want to do? Calculate the Fisher matrix for supernovae?
Yeah.
Okay, so yes, there is. So supernovae are these contours, the green ones. I got a Fisher matrix from Renée Hlodzik. And she, I think, has computed this together with Dan Skolnick using Cosmosis or some Cosmo-MC Cosmosis hybrid. But the Fisher matrices for the supernovae, they are in here. So if you're interested in, let's go back here. There is probably, let me see, 3x2 points, stage 3, clusters. This is strong lensing because it came from Tom Collett. This is supernovae because it came from René. So there is a Fisher matrix in the repository, and you would just have to code this part up. This might be in the repository or it might not be in the repository. But for supernovae, you just get those 4 parameters. You get a 4x4 Fisher matrix, and then you get you can create a chain in omega matter H0, W0, and WA. Yeah. But only for LST year 1 and LST year 10, right? If you have something else in mind, you have to go through the whole machinery that René went through. Okay. Any other questions? Yes? Yeah, they are already there. I did not include any advice on how to compute the covariance matrix in this. This is really the thing that you have to parallelize on the supercomputer. You have to patch it together. You have to run check routines, whether the covariance matrix is well behaved in many aspects, positive, definite. You check for the condition number, whether it's ill-conditioned or not. And then usually it is not well behaved, and then you have to do it again. And at that point, you have to tweak things, and you have to somehow know what to tweak. It's very hard to give general advice on how this is, how to get a good covariance matrix always. So that's usually something that if somebody really wants to do that, they should come and talk to me or others. But I did not include this. It would require more details than what I've already written in the README, many more details. So, and also a much larger part of the code. So if we look at, this is Cosmo-like light, which allows you to compute a data vector. It's very self-contained, but it does not include any of the covariance files, which is several more still. So I didn't include the covariance matrix routines in here. They're also a bit more experimental compared to this. This is relatively solid. Okay. W first. This has to go faster. Okay. All right, come on, W first. Where are you? Yeah, so I spoke to a couple of people here, and W first seems to be one of the lesser known surveys, but it is very cool and interesting, and so I thought I'd give a very quick overview on it. There's been a couple of white papers. This was one that I wrote, partnering space and ground observatories, synergies in LSST and W first, and this is within a science investigation team of W first that I'm part of. So NASA, always when they have one of these very large missions, they create science investigation teams for various aspects. This is one in cosmology. Actually, I mean, there's actually many more people in here who are not part of the science investigation team, who just thought this was interesting. So I quickly go over some of the aspects that I mentioned here, because W first and LSST is a really interesting combination. People talk a lot about W first, about LSST and Euclid, and that happens mostly because they are happening on the same time scale. But W first will only be 3 years later, and it is a 2.4 meter. It is very powerful in space. It can take part in this overall synergy choir of LSST, W first, and Euclid. So it should not be neglected. So this was a very quick overview of what's out there. This has been completed in terms of surveys. This is what's happening now. This is Euclid, W first, LSST. These are now start dates. I think I've shown a similar slide already, but I had end dates. And the W first is on track to launch in 2025. Sometimes you hear these news stories about, the administration has canceled W first. Yes, it has tried that twice. But Congress, and Congress is the entity that controls the money, has put it back in. And so far, every year, the whole W first endeavor has been fully funded. And that's actually quite rare. So every time the amount of money that's been asked for, okay, 1 year it was a little bit less, has been appropriated by Congress to the overall team. And that's not the science investigation team. Here I'm talking about the project, the people who are building the instrument. So that's $3.2 billion, and this year we, I think, asked for 520 million, and they have also been, they seem to be in the budget. So this is the comparison. WFIRST is going to be deeper, going to be less area, but we'll get to that later. It was the top-ranked space mission of the Decadal Survey in 2010. What is the Decadal Survey? It's actually quite interesting. It's going on right now. This is a community effort in the US where all the scientists submit white papers and ideas. What should the community fund over the next 10 years? So everybody can submit a white paper. There is a very large panel, 2 chairs. There are sub-panels, etc., on cosmology, on galaxy formation, on all the other subfields. And they read these white papers, they condense the information, and then they make recommendations. So it is really a grassroots approach, and I do think this is very nice and valuable. This time in particular, also junior members are strongly encouraged to contribute, and also on the panels, you can see there are some junior members who are sitting there in addition to very famous National Academy science members. Okay, so WFIRST is currently in phase B, but is almost, well, there is a design review coming up, and then it will enter phase C, and phase C is important because that's when a mission is considered becoming real, and NASA is kind of committed to actually doing it. So we're almost there. It's a 2.4 meter Hubble-sized mirror. So it is much larger, for example, than Euclid, I mean, twice as large. And it was repurposed from the US spy agency. So the US spy agency had these mirrors sitting around. Not the NSA, the National Reconnaissance Office. That's the ones in space. They had these mirrors sitting around. There were 2 exquisite space-qualified mirrors that they declassified and then gave to NASA. And now NASA could have built 2 WFIRST, but they just do 1. So it's a multi-purpose dark energy mission. It's a multi-purpose mission from dark energy to exoplanets. And the most important thing here is really it covers a wide field. If you look at an observing timeline, you can see that this is really a mix of many, many different things. So there is a guest observer program where individual groups and PIs can suggest, I want to use WFIRST for a month to do X, Y, and Z. You're not going to get a month, but there is time allocated for PI-led small projects. There is a high-latitude survey. That's the cosmology part, high-latitude imaging and spectroscopy. So there is a GRISM, a lower resolution spectroscopic instrument on WFIRST, and there is this very nice infrared camera. And so both of these are then being put together, observing the same area, and that will be the high-latitude survey. There is a microlensing aspect. There is a supernova program. And then there is people looking into the galactic plane and also for exoplanets. Now, the exoplanet part, that is now only it's no longer a science-grade instrument. It's just a demonstration-grade instrument. But and that means because we had to save some money somewhere. But nevertheless, this would be a very, very interesting demonstration instrument. And of course, if it works fine, the people building it are doing their best. If it works fine, then you will do science with it. That's very clear. This is a quick overview of what it can do. So it has several filters ranging from the optical here to the infrared, so up to 2 microns. Some of these filters, you will see they overlap. Some of these are narrow band filters. That allows you to get very good photo Z. Some of these are actually quite broad. This is the microlensing filter. And this is really a photon bucket. This is the filter where you collect a lot of photons at the same time. This is the GRISM. Yeah, you can see the field of view. It's roughly 0.3 square degrees. Not as big as DCAM, but much, 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 much larger than Hubble Space Telescope, for example. Right, and that's the comparison right here. So this is basically one image of the Hubble Space Telescope. That's one field of view of the Hubble Space Telescope. And WFIRST does all of that at once. So all these squares would correspond to of order 2 WFIRST images. Ah, okay, yeah, here you can see that. W first, HST. W first, HST. Otherwise, they're actually relatively comparable in terms of resolution. This is a dark energy plan, so if you're mostly interested in dark energy, you should care a lot about the high latitude survey, which is decomposed into the spectroscopic part and into the imaging part. And those numbers, yeah, okay, let's not dig too deep into them. And the supernovae survey as well. So similar to DES, there is supernovae involved, which I think is not true for Euclid, for example. So supernovae in space just allows you to observe them in the infrared. That's not possible really from the ground, and that is actually quite interesting. So the supernova community was quite happy with that. Unfortunately, we lost the IFC spectrograph capability. Again, there were some cost savings that had to be made. The reason for that is because JWST, the James Webb Space Telescope, has such a big cost overrun right now. It was originally proposed to cost, well, to cost much less. Now it costs kind of 9.6 billion. W first has to keep on track budget-wise. It has to stay within the 3.2 billion cost cap. And if there is a projection that it might run over, then they ask you to descope. And so in the last descope, the survey time was reduced a little bit. One instrument was taken out. But that's really not so critical. If the instrument works fine, they're going to extend the mission anyhow. Right, this is actually shown here. So science operations would start in 26. They would last 5 years nominally. But if you know how long the Hubble Space Telescope has been around, right, you can imagine that they're not going to abandon something that works well. If it doesn't work well, of course, then that's a different question. But something that operates very, very nicely, this doesn't have expendables. So I think there is no gas to repoint the telescope, nothing like that. There's no coolant. There is a reaction wheels only. So if those break at some point over time, then this can cause an end of the mission, but otherwise not. Yeah, but we also I also wanted to talk about LSST and about the combination of LSST and W first. So just a very quick overview of LSST. This is just a fake image, but now if you actually look there at the webcam, I do encourage you to look at the webcam, you will see that it almost looks exactly like that. They've started building the dome. You can now see white structure on the dome already, and the webcam gets updated every whatever, half a minute or so. So LSST, also one of the science cases is dark energy. That's the desk science collaboration. There's 6 different cosmology working groups. I am the co-lead of weak lensing. And then there's lots of enabling analysis working groups and also several working groups who help provide infrastructure like numerical simulations and other simulations, etc. This is a very nice collaboration to work in. I can only encourage you to have a look at that. Timeline of LSST. This is very complicated, but in principle, full operations would start here at 2022. So roughly 3 years before W first. And that's actually quite interesting. So how do we optimize this? How do we explore synergies? So you can put yourself at the timeline when W first launches, 2025. And by that time, LSST will have operated for already 3 years. You will know what is limiting LSST, right? What are the main problems of LSST? Is it photo Z? Is it shape calibration? What is it? And W first is so versatile that it can tackle these problems depending on what they are. So it's the exact right timeline that these 2 missions are ordered in. Okay, we've seen this slide. That's the challenge, or those are the challenges that we face when we want to optimize such a survey. I'm showing this because when you do such kind of a likelihood analysis, I wanted to point out something that I didn't get to talk about is that you want to do this blindly. You want to do this through a blind analysis. And actually, I thought I wouldn't be so late in the lecture, and I wanted to have an exercise here for you to discuss what's this blinding and why is it useful, and why do we actually want to do a blind analysis with these surveys, with LSST and W first. But that's something that you'll have to do over coffee. I would really like you to think about what are the pros of blinding your data, what are the cons of blinding your data. There are some cons, but if you want to make your results credible, I think having a blinding scheme is useful. I'm just going to skip forward to the actual slides that I wanted to show for combining them. Not this, but this. Yeah, okay. So this is the machinery that we've actually built. We have a W-first, how's it called, exposure time calculator that tells you, that gives you different versions of the survey. We then go to the candles catalog. That's the only catalog out there that actually resembles the depth that W-first will reach. And you can get a realistic galaxy sample only over a small part of the sky, but you can get a realistic galaxy sample from the candles catalog of what W-first will see over a much larger area. And then you can get your redshift distribution from that. Then you can get a covariance matrix with these redshift distributions. You have to decide on the probes. And you do that for W-first and for LSST, and you can do some joint contours. Now, originally, the W-first footprint would be rather small, 2,000 square degrees only. That's one of the that's basically currently the nominal survey. And for example, Euclid is going to cover 15,000 square degrees over 6 years. You can see these 2,000 square degrees, you get them in just 1.5 years. So this is much, much, much faster. And you are observing these 2,000 square degrees in actually 4 narrow infrared bands, whereas Euclid does a fair fraction of this survey is 1 broad optical band. And that's a difference of well, that's actually a difference of 16, because not only if you go from 1 band to 4 bands, right, that's a factor of 4, but if you pick 1 band that is as broad as these 4, you get 4 times as much photon throughput. So it's a factor of 16 in speed that you could gain if W-first were to adopt the survey strategy that has 1 very broad filter. And 2,000 times 16 in just 1.5 years, that's very, very interesting. This is also much, much, much deeper. This is at LSST depth. Euclid is not quite going to reach LSST depth. So I'm not saying this because I'm more a fan of W-first than Euclid. I just want people to understand that W-first is quite a powerful instrument that's going to be online in 2025. And it's so far, the data will be public immediately. So that's quite nice. I don't know if that's going to stay that way, but that's the current plan. Data is just public immediately. So let's have a look at one of the, the main question is, does W-first have the option to use such 1 broad filter in its observations? And yes, it does. There is, and thanks to the microlensing people who always think that we dark energy people don't like them because they take survey time away from us, but I do like them because they put this very wide filter on the W-first. That's how they observe microlensing events. And this filter here is roughly 4 times as broad as the 4 filters that W-first would use otherwise for the 2,000 square degrees. So there is the idea within our science investigation team, well, let's explore how fast can W-first map all of the LSST area in this 1 band. And that's actually quite impressive. So this here is survey time of W-first, and this here is the limiting magnitude that you can achieve in this wide band. And you can see that already after something like 0.5 years, so 6 months, you can reach LSST weak lensing depth. You get images of 95% of the LSST weak lensing sample over the whole LSST area. 2 full LSST, to 95% completeness, which is almost the full depth of LSST. I mean, some galaxies are just very hard to get in the infrared when you've observed them in the optical, right? So it takes longer to reach 99% completeness. But still, this is amazing. This is 18,000 square degree survey, and it takes 6 months down to LSST depth. Just 1 band. You don't get the 4 bands. It's just 1 band. Yes?
So the W-first doesn't plan to cover the whole parts.
It does not plan, but it could.
If it would
Yeah.
To take that.
Right, and so that's maybe another thing to keep in mind. The W-first survey strategy is not yet defined. For many, many other experiments at this stage, it would be defined, but there's no real expendables. You don't have to optimize things. There's great flexibility in defining this, and this is something that we are going to put out as a suggestion in the near future. So, yeah. This is what happens if you do such a W-first wide survey and then you combine it with LSST. But how exactly the figure of merit looks like, I don't think that's so important. I think what's much more important is to note that if the high latitude survey is given 1.5 years, you can just spend 0.5 years on a very wide survey program and then spend the rest of the time, so 1 year, on doing a smaller patch but deeper in multiple filters, and then you can get a very nice calibration sample. I mean, that's not really a calibration. It will be 1,400 square degrees. That's a serious survey in and itself. Okay, so there's many more papers on this, on the HLS survey as it is defined right now, one led by Olivier Doré. He is the PI of the science investigation team. But the main takeaway that I really wanted to convey is that, first of all, it is on track to launch in 2025. It is funded. The funding always only happens year by year. That's how NASA works. But there is lots of support in the relevant entity, namely in Congress. There might be a little bit less support in the White House. But the nominal survey is currently 2,000 square degrees, and it is designed for exquisite systematics control, because that's what you get if you have these 4 different bands. But if you want to do something wide, you can cover LSST area to LSST weak lensing depth in like just 5 months. And that's very interesting. And if you were to do something like that to cover 18,000 square degrees, that enables a lot of other interesting science cases as well, with CMB, with radio surveys, etc. So having such a wide survey data set, and perhaps even it is interesting to do an all-sky survey with W first, that would take a little bit longer, but still 1.5 years roughly. It would be a fantastic data set to work with. And I'll stop here. Thanks, and sorry for this slide.
Questions for Tim? Yes. Supernova?
Supernova is fine. I will defer. I will just name names.
Okay, so since you didn't have much time to talk about it, can you talk a little bit about the blinding and
I love to.
the pros and cons?
Thank you. Thank you so much. Where do we go? Blinding, here. Okay, what's this blinding? Why do we want to do it? This is actually one of the nice plots that I wanted to show. It's again a history plot, so I'll probably fail. But it's 1960 to 2010. You can see the neutron lifetime in seconds, and these are different measurements coming from different experiments. And you can see that there's like one experiment that does something, and then there's error bars very similar, and suddenly there is a drop. And the drop happens because there was a new experiment that came around that actually did something, well, that was just better. And then many, many others follow the lead of that experiment. It's very, very similar again. And then again, there's a drop. So you can see that experiments who follow the main lead of these of this groundbreaking experiment, they tend to be very, very within these error bars. I mean, this is amazing that this mean doesn't shift more, right? You would expect that there is fluctuations within this, just statistical fluctuations, but no. People are informed by what they think the current standard is, right? So that leads to something like experimenter bias. You have expectations what your experiment should give. And in order to counter these expectations, you should actually blind your analysis as much as possible. Now that has a downside, because if you blind your, because sometimes expectations are also good, are also important, right? You want shear calibration to be better than X, Y, and Z. That's an expectation, and you should be able to check that. So that falls under the regime of null tests, and we've mentioned null tests, and you have to define this very exhaustive list of null tests beforehand, but you should never really have a look at what is at the thing that you're really after in terms of physics. You don't want to iterate on the important outcome of your experiment. That should not influence you. So it is important to blind your experiment and to do that smartly through a suite of null tests, and then to unblind the experiment in stages until at the very end, when you unblind and you find something that is discrepant with what the state of the art is, you still, and then you should not go back, right? So you can go back, but it is a separate analysis at that point. So you should actually make a statement in your paper, what is the outcome of the blind part? And if you then go back and you do additional tests because you're worried, you should state that this is no longer happening, this has no longer happened blindly. This was now informed by your bias that you expect something that, this other groundbreaking experiment had before. So it's not a perfect solution to this problem, right? But experimenter bias is real, and we have to think about how to avoid it in these analyses. Because in particle physics, it's like if your experiment hasn't been done blind, people don't trust you. At least that's what I've been told by. Okay.
What are the cons on blinding?
Well, so people who argue against blinding, first of all, say, this is so hard. This takes so much effort to blind all these different stages, right? You have to blind the catalogs, you multiply the catalogs, you have to define a mathematical scheme how to do it. Sometimes they're also a little bit, but come on, if I blind it, all my intuition is gone, right? I know how this works, and I should be able to see everything because only then the experiment is going to work properly, right? So yes, it costs time, it costs effort, you have to think about it. So it might delay the experiment a little bit. Those are cons. But I think the latter argument, that your intuition is somewhat no longer effective, that's exactly what you want, right? You want to be rather neutral in those aspects. Your intuition can go into the suite of null tests. That's where your intuition should go, all of it. Yeah.
There's also confirmation bias, which is related. And there's a very scary example of cold fusion. You're probably not old enough to remember cold fusion. Any further questions? Yes, Peter.
When you were talking about the W first and LSST synergies, those forecasts you showed are like multi-probe. You're not. The synergies include things like, okay, I get better spectroscopy, so I improve the photo Z, or I get better shape measurements, because there's no seeing, and those are not included there, I think.
Right, very good question. Yeah, and I'm very glad that you asked this because it immediately shows that you paid a lot of attention to the lectures, right? Don't take forecasts for granted. Ask about what went in those. These are very simplified. That's actually just, if you have space-based observations, you get an increase in number density. I take the area from LSST. I take the increase in number density that you get because you have W first. I take the deeper redshift distribution that you get because of W first. And then it is only a statistical analysis. This actually does not include systematics yet. And you are right that there is additional gains you would assume in the systematics regime when you have overlapping ground and space, right? Shape measurements are easier from space. If you have infrared information, photo Zs are going to be better. So the relative gain will be even more prominent when you include systematics, yes. Yeah. Okay. Oh, very nice. I'm happy.
More questions? Okay, don't see any hands up. So this is the last lecture of the school. Oh. So on behalf of the organizers of the school, so Raul, Merdad, Paolo, Creminelli, and myself, I'd like to thank, first of all the lecturers, Tim, Marco, and all the others that came here to take their time to lecture to you about observational cosmology. So thank you very much. And most importantly, thank you all for coming. And I hope this was useful for you. I think it was. It was useful for me. So yeah, so I think this was a very nice school. I'm very happy with this school. Okay, so thanks for coming.
And I really want to thank Rogerio again in particular for, organizing all of this and sitting through all of the lectures and asking so many questions. No, it was really a great experience for me, and I know for you probably as well.
Thank you.
Yeah,
thank you all. This is not part of the school, but there's seminar too.
Okay. Lunch, yeah.